Hi students, we are right in the middle of dimensional analysis and we left off on problem number 5. And problem number 5 says, what is the mass of 1.34 moles of carbon dioxide and what is the mass of carbon in this sample? So in order to work problems like this, we want to break it down into parts and we want to start with the given. So we have to take a look at this problem and see what kind of information it gives us. And that is 1.34 moles of carbon dioxide. So we're going to start by writing down the given. So we have 1.34 moles of carbon dioxide. And this right here is our given. And we want to go from moles to where? What other unit are we going to? Moles to mass. The question says, what is the mass? Now, we have a conversion factor that relates mass to moles. And our conversion factor, my cat is saying hi to you guys. Hi, Daisy. Now be quiet. Okay, so the conversion factor that we want is the molar mass. Because the molar mass relates grams to moles or moles to grams. And grams is a unit of mass. Now, if we're letting our units guide us, we'll take a look at the moles here. And we'll know that we want to get rid of that and go to grams. So do we need to put the moles in the numerator of the conversion factor or the denominator? In the denominator. Because that's going to give us moles of carbon dioxide divided by moles of carbon dioxide, and anything divided by itself is what? Is 1. Okay, so if you guys need to write the given with the denominator in it, just to remind yourself that it's there, you can go ahead and do that and put a 1 on the bottom. If you don't need it, okay. All right. So for the molar mass, remember we're going to put a 1 next to mole wherever we have it. And then we're going to put how many grams of carbon dioxide we have per every 1 mole. And we figured this out in the last problem where we said that the molar mass for carbon dioxide is 44.009 or 44.01. So we can just write 44.01 here because that would give us 4 sig figs, which is 1 more than the given, and that's good enough. So we see that we're in the units that we want to use. We're in grams of CO2. So we go ahead and do the math. And if we do correct significant digits, what we're going to end up with is 59.0 grams of carbon dioxide. Now originally maybe you had 58.96 and then you knew that you had to go ahead and make this 3 sig figs, so we'd count over 1, 2, 3. So we know that we're going to end our answer right there because that would be 3 sig figs, except there's a 6 next to that 9, which means you got to round this up, which would make it round up to 10, which would give us 59, but you still need 3 sig figs, so you got to have that 0 there. Okay, so that's the first part of that problem. And then it says, what is the mass of carbon in this sample? So we don't have carbon here, we have carbon dioxide. So we need to go from one substance to another substance because carbon dioxide and carbon are completely different. So what we're going to do here is we're going to start over. So I'm going to give the given down here again. So that's 1 mole of CO2, and again, that's the given. But this time, we don't need to go to grams of CO2. We need to get from CO2 to a different substance, carbon. But we're still going to need a conversion factor to do that. So we want to get rid of moles of carbon dioxide. So does mole of carbon dioxide go in the numerator or the denominator of our conversion factor? Again, it goes in the denominator. So we have moles of carbon dioxide. Now, the question is asking you, what's the mass of carbon? So somehow we have to get from carbon dioxide to carbon, and this conversion factor is where we're going to do it. Whenever you need to go from one substance to another substance, you want to relate moles to moles. And this conversion factor right here, this conversion factor is called your mole to mole ratio. And when you get stuck in a problem, your brain should go ding, 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 I'm stuck. So I'm probably at the mole to mole ratio part. And this is a little bit weird for some students, and that's okay, you're learning. Now, if you have 1 CO2, you just have a single carbon dioxide floating around. If you have 1 of those, how many carbons do you have in that single CO2? You just have 1 of them. So for every 1 CO2, you have 1 carbon. So if you want to, for a second, put your finger over mole and mole so you don't see that there. What we would be saying is for every 1 carbon, for every 1 carbon dioxide, we have 1 carbon. And if you have a dozen carbon dioxides, if you had 12 carbon dioxides, if you had 12 of those, how many carbons would you have if you had 12 carbon dioxides? Well, you would have 12 because every carbon dioxide carries with it 1 carbon. Okay, so now I've got to erase that and that and go back to, if you have a mole of carbon dioxide, which is just a quantity, like 1 of them or a dozen of them or a gross of them, in every 1 mole of carbon dioxide, you're going to have 1 mole of carbon. Okay, and again, put your finger over the mole in the mole, and you'll see that the relationship will make sense. Okay, so now we've canceled out moles of carbon dioxide, and I need to let my cat out before she bugs me to death. You crazy cat. Okay, she wasn't going to stop. So we're in moles of carbon, but that's not where we want to be. We want the mass of the carbon. Now, when we're in moles and we need to get to mass, we know what conversion factor we're going to need to use. We're going to need to use a molar mass. Okay, so we need to get rid of moles of carbon and we need to get to grams of carbon. So for the moles of carbon in our new conversion factor, do we want to put it on the top or the bottom? On the bottom, because then we have moles of carbon divided by moles of carbon, and anything divided by itself is what? Is 1. So this is our molar mass of carbon right here. Okay, so whenever we do a molar mass, we put the number 1 next to our carbon, and then we put grams of carbon on the top. And if you look at your periodic table, what you'll see is carbon has an average atomic mass of 12.01. And that's going to bring us to our answer, which is 16.1 grams of carbon. So there's 16.1 grams of carbon in 1.34 mole of carbon dioxide. Now I want to warn you guys about the mole to mole ratio. It won't always be a 1-to-1 ratio. We'll see that quite often in this lesson, but we'll definitely come to a point where it's not 1-to-1. There's other numbers there, and you want to make sure that you get that right. Okay, so the next problem says that we have 9.29 grams of sodium chloride, and we want to know how many moles of sodium chloride we have in our 9.29 grams of sodium chloride. So you need to figure out what you need to write down first on the paper. And that's going to be your given. So you're going to have 9.29 grams of sodium chloride, and that is your given. And the question asks us for moles. Now, we want to get rid of grams and we want to get to moles. So we have grams in the numerator here. Remember, there is a 1 in the denominator for our given. So do we want to put grams in the numerator or in the denominator of our conversion factor? We want to put it in the denominator because we're letting our units guide us, and we need to get rid of grams of NaCl, and grams of NaCl divided by grams of NaCl is what? It's 1. Anything divided by itself is 1. So this conversion factor here is going to be the molar mass of NaCl. Okay. And we want to go to moles, and whenever we have a molar mass, we have the number 1 next to moles. And I say that because the molar mass is different from the mole to mole ratio. Okay, so where do I find the number that goes in the bottom right here? Well, we already calculated it on the previous slide, and we found that 1 mole of NaCl is 58.443 grams. So we have 1 mole of NaCl per every 58.443 grams of sodium chloride. Okay, so how many moles is what we're answering in the first part. And so if we go ahead and we do the calculation on that, what we'll find is that we have 0.159 moles of NaCl. Now, if you had an answer of 0.158 because maybe you used 1 fewer significant digits, is that okay? Yes. Because remember, the last digit is where we have some wiggle room, and that is our best estimate there. And so you're okay there as long as you've got 3 significant digits there and you have 0.15 something. Okay, now it says how many moles of sodium are present in the sample. And remember, sodium is completely different from sodium chloride, even though we use those two terms, sodium and sodium chloride, interchangeably in real life. So what we're going to do is start the problem over again, even though we could continue on from what we had already written. But I want to give you guys some practice. So how many moles of sodium are present in the sample? Well, you would start with what you're given. So you're given 9.29 grams of sodium chloride, so that's the given. And we want to get rid of grams of sodium chloride, so we're going to put 58.44 grams of sodium chloride in the denominator there, and 1 mole of sodium chloride in the numerator there, because that's the same conversion factor there. It's the molar mass of sodium chloride. And our grams cancel out. Okay, so now we are in moles of sodium chloride. But the question says how many moles of sodium, not sodium chloride, are present. So we need to switch from sodium chloride to sodium. So whenever we need to switch between substances, even if they sound very similar, like sodium chloride and sodium, we need to do a special conversion factor called the what? Mole to mole ratio. So again, if you feel like you're stuck and you don't know where to go, you're probably at the mole to mole ratio portion. So we want to get rid of moles of sodium chloride. So are we going to put it in the bottom of our next conversion factor or in the top? In the bottom, that's right. So we have moles of sodium chloride, and on the top we have moles of what? Where are we going? We're going to sodium. And again, sodium chloride and sodium are different. Now here's the place where we need to find the ratio of sodiums, the Na, in every sodium chloride. And again, I want you to put your finger over mole and mole, okay? So put your finger over that and go ahead and tell me, for every 1 sodium chloride you have, how many sodiums are in that 1 sodium chloride? Just 1, okay? So again, we have the ratio of 1 to 1, but it won't always be 1 to 1. So again, it's just a ratio. So if you have 1 sodium in every 1 sodium chloride, you've got 1 mole of sodium for every 1 mole of sodium chloride. And this is going to give us exactly the same answer as above, because all we did was we took this right here and we multiplied it by 1 and we divided it by 1. Now obviously the math won't always be that easy when we come to the mole to mole ratio, and you guys will see that in a little bit. But this is really good practice at setting up these equations and doing this dimensional analysis. Okay, so we're moving on to number 7, and it says how many oxygen atoms are there in 5.62 grams of carbon dioxide? Okay, so the first thing you have to figure out is what are you going to write on your paper? So what is the given? The given is 5.62 grams of carbon dioxide. And you guys will see that these problems will follow the same pattern. So that's why I keep writing out to you, this is the given, this is the conversion factor, this is the mole to mole ratio, so that you can see the patterns. So we have grams, and whenever we have grams and we want to solve one of these problems, we go from grams to what? to moles. We have to get to moles to do anything with it. And in order to go from grams to moles, what is our conversion factor there? When we relate grams to moles or moles to grams, the conversion factor is what? The molar mass. Okay. And whenever we do the molar mass, there's going to be a 1 next to mole, and then we have to figure out how many grams does a mole of that substance weigh. Well, we already figured this one out, and we said that it was 44.00. Now, the question is not asking for moles of CO2, it's asking for oxygen atoms. But let's just take it one step at a time before we get overwhelmed. And I don't know how to go exactly to oxygen atoms here. Yes, you do. Okay, now we're in moles of carbon dioxide. And now if we're feeling like, oh my goodness, I don't know what to do from here, I'm stuck. Okay, an alarm bell should go off in your head that says ding, ding, ding. You're probably at the mole to mole ratio portion. Okay, so we want to get rid of moles of CO2. So we're going to put moles of CO2 down here. And since we're at the mole to mole ratio portion, we probably want moles and moles because it's a mole to mole ratio. Now, we're going from CO2 to which substance? To oxygen. And it specifically asks you about oxygen atoms. So we're not going to do the oxygen molecule O2. So right here, this conversion factor is our mole to mole ratio. Okay, so looking at this, we want to ask ourselves, how many oxygens do we have in every CO2 molecule? And if we take a look at the drawing, and we cover up with our finger, cover up the mole, because that bugs a lot of people there. Just ask yourself, how many oxygens are in every carbon dioxide? And you'll see that you have 2 oxygens per every 1 carbon dioxide. So if you have 1 mole of carbon dioxide, you're going to have 2 moles of oxygen. Okay, so now I've got rid of moles of carbon dioxide, and I'm in moles of oxygen. But the question asks for oxygen atoms. So that's not exactly like before where we went from moles to grams, but we can do this. We can let our units guide us. So we know that if we're not in the right unit, we need another conversion factor. So we go ahead and write our conversion factor with moles in the bottom because we want to get rid of moles of oxygen. And if we have 1 mole of anything, cars, boogers, oxygen, how many of those things do we have? We have 6.022 times 10 to the 23rd. This right here is Avogadro's number. Okay, so we've gotten rid of moles of oxygen, and now we have atoms. And I can't fit atoms of oxygen there, so we'll just put atoms oxygen right there. And then we do the math on that. And if you guys have forgot how to do exponents on your calculator, now's a really good time to review that. Okay, So what we're going to get for our answer has 3 sig figs, and we have 1.54 times 10 to the 23rd oxygen atoms. Now, if we look at this number and this number and this number and this number, it looks like we have one significant digit there. But the thing about those numbers is they're exact, so they have infinite amounts of significant digits. So we don't count those. We just ignore those and we look at our other values, like this one and this one and this one right here. Now 44.0 has 4 sig figs and 6.022 has 4 sig figs, so we go with 3 sig figs right here. Okay, so here's our answer right here. Now number 8 says your nurse gives you 10 milligrams of morphine, and morphine is a big old molecule. It's this down here, C17H19NO3. And if you look at this molecule, you see something funky. It's right here. And these are bonds that are coming out at you. So it's hard to draw those in 2D when it's a 3D molecule. So when you see those bolded bonds, it means those are coming out at you. They're not crossing the bonds in the other rings. And remember the points, at the points of all of our structures there, we assume that you know that there's a carbon there, and we assume that you know that carbons like to have octets. So if they're only bonded to 2 other carbons, like our carbon in the middle there, then we assume that you know that there's a couple of hydrogens on there. So that's just a little bit of a review of structures there. So back to the problem. What we want to do is we want to figure out what we're going to write down first. And what we're going to write down first is our given. So we have 10 milligrams of morphine. And it asks us, how many moles is this? Well, usually we can go right to the moles, but here we have milligrams, not grams. So we can't use the molar mass of morphine right away to go from grams to moles. So we have to get rid of that milligram first. And so that means that you're going to put it in the bottom. And you want to get to grams because then we can relate grams to moles, which is what the first part of the question is asking us to do. So which one is the bigger unit, grams or milligrams? It's grams. So you want the one next to grams, and you want to ask yourself, how many milligrams can I fit into a gram? How many milligrams per gram? And this is one of those things you should know by this point, that there are 1,000 milligrams per every gram. So we've canceled out our milligrams here, and we're in grams. And now we can get rid of grams and go to moles because we have something called the molar mass, and that relates grams to moles or moles to grams, okay? So we have grams of morphine here, and we have 1 mole of morphine here. And what we would need to do is add up the mass for each of those atoms in this molecule. So carbons weigh 12.01 on average, so you do 17 times 12.01, and you'd add that to 19 times 1-ish for the hydrogen, and then you do the nitrogen and the oxygens. And I've already done that for you guys, so I'm hoping you'll trust me that it's 285 85.34. And if you want to go ahead and add up the molar mass for morphine yourself, you're welcome to do it, or just go ahead and Google it or look it up on Wikipedia, and you'll see that it's about 285, just like I said. Okay, so the first part of the question asks us how many moles, and we've gotten rid of grams, and we're in moles of morphine. So you'd have 10 divided by 1,000, hit equals, and divide that by 285.34, and your answer should have 3 significant digits, and we will find that we've got 3.50 times 10 to the negative 5. So if your calculator says that number, but it has a few zeros in front of it, you're probably right. You just have to take that decimal right there and move it to the left 5 times, and you'll get that same numerical answer. And we always need to have the label on this. So we have 3.50 times 10 to the negative 5 moles of morphine. So this right here is our answer, and we want to make sure that we have the correct number of significant digits. So we have 3 there, and then these ones are exact, so we don't count those, and then we've got 5 there. So our answer has how many? 3. Make sure you've got your label so you get your points there. Now the next part of the question says how many grams of oxygen are present in this dose of analgesic. So what we can do is we can start the problem all over again, or we can continue on from moles of morphine. So I'm going to erase this right here and show you that we're going to continue on from here. Now, if you guys want to write the whole problem out again, that's totally okay, but you'll see that you'll have the first 3 steps are exactly the same. Okay, so now we're in moles of morphine, but we want to go to grams of oxygen. And most of us don't know the direct relationship between moles of morphine and grams of oxygen. And we have to think, okay, we're going from one substance to another substance. We're going from morphine to oxygen. So I'm kind of stuck right here, not knowing what to do. Plus, I'm going from one substance to another substance. So ding, 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 ding. What kind of conversion factor should I have? I should have a mole to mole ratio. Okay, so that's the type of conversion factor we have here. So we want moles on the top and we want moles on the bottom. So the question is, for every 1 mole of morphine, how many moles of oxygen do we have? Now, if moles bothers you, again, cover it up and ask yourself, if I've got 1 molecule of morphine, all I've got is that C17H19NO3, how many oxygens do I have? Cover up those moles and ask yourself, if I've got 1 molecule of morphine, how many oxygens? You've got 3. So you can see here that the mole to mole ratio is not always going to be 1-to-1 like it was in the previous slide. So in question number 7, we had a ratio of 2-to-1, and for this question we have a ratio of 3-to-1. Okay, so now we've gotten rid of moles of morphine and we are in moles of oxygen. And the question asks us for grams of oxygen. So when we're in moles and we need to go to grams, what conversion factor do we use? So I'm just gonna keep on going with the rest of the problem down here. So moles to grams or grams to moles, what you're gonna need is the molar mass. So we're going to go ahead and write in every 1 mole of oxygen, and that's the single oxygen, not the O2 molecule. What does that weigh? Well, this is where you would just look at the periodic table, and off of the periodic table, it would say that 1 mole of oxygen weighs 15.999 grams. Or you could ask yourself, what does 1 single oxygen atom weigh? Well, that would be 15.999 AMU. So we've got the same number there, just a different unit. Okay, so the moles of oxygen cancel out. And what we end up with here is 0.00168 grams of oxygen. And that's got 3 sig figs, like the original number there. And it's got our unit, grams, and what is our substance? Oxygen. Okay, that's it for this video. You guys, if you find any errors in my math or significant digits, please email me and let me know so I can correct it or answer your questions. And in the next slide, we're gonna move on to something super exciting. More problems with more math, yay! Okay, bye-bye.